In Chapter 13, Section 2, we talk about what we call Euler paths and Euler circuits. In 13.3, we're going to talk about Hamilton paths and Hamilton circuits. In 13.1, we introduced graph theory, and we talked about general paths and circuits, just what that general definition is and what that looks like. Now we're moving on to specific types of graph theory. I know that this looks like Euler. It's German, though. He was a mathematician. It's pronounced Euler. Okay, true or false, A, B, C. These are review questions about general paths and circuits. Every circuit is a path. Remember that a circuit begins and ends at the same place. So if I can get from here to there, that's a loop, not necessarily a circuit. Let's do it this way. Let's do A, B, C. So if I can travel from A to B to C and back to A, that is both a path and a circuit. So yes, that's true. Every circuit has to first be a path. I have to be able to travel it. And then for it to be a circuit, it has to start and stop at the same place. Now, what are my requirements for a path? Does a path have to go through vertices only one time? Do we talk about that at all? No, in general, my path can wander around and retrace and backtrack and not include vertices. It just doesn't matter for general pathways. What about C? A path must go through edges only once. Well, no, again, I didn't put any limitations on what a path needed to look like. Okay, but an Euler path is a more specific type of path. An Euler path is a path that travels through every edge of a graph exactly once and only once. So Euler paths focus on edges, focus on those E's. Euler paths focus on edges. An Euler path is a special type of path. It travels through every edge on my graph exactly one time, not more than once, and it doesn't skip any. An Euler circuit is just an Euler path that starts and stops at the same vertex. So it's a circuit that travels through every edge of a graph exactly one time. True or false? Go ahead and answer these 3 questions about Euler paths as either true or false, based on the definition we just gave. Remember our definition defined an Euler path as a path that travels every edge exactly one time. So 5 out of 6 edges is not good enough. 5 out of 6 edges once and through the 6th edge twice is not good enough. At least once is not the same thing as exactly once. At least once means it could have traveled an edge 2 or 3 or even more times. So the importance is every edge exactly one time for an Euler path. Okay, so we are going to determine if these sequences are general paths and circuits, and if they are they Euler paths and or circuits? Okay, the first one. Could the first one be a circuit? Well, no, it just couldn't, because I start at D and I end at C. So I know it's not a general circuit, and I know it's not an Euler circuit. Can't be a circuit. Let's finish out checking to see if this first one works as a path. It has to work as a general path if I can consider whether or not it's an Euler path. So let's start to see if it's just in general a path. Can I travel from D through the set of vertices to C? So let's trace it with our pen. D to E, to G, to F, to A, to B, and then to C. Yeah, that absolutely works. I can get from there to there. That's a path. Is this path an Euler path, though? Well, no, it's not an Euler path because I didn't travel every edge. I missed 1, 2, 3, 4 edges total. Okay, let's look at the next one. I'm going to color code these so you can kind of go back and see if you want to. The second one, could the second one be a circuit if it works? Well, yes, it could, because it starts at F and it ends at F. So it could be a circuit. So let's check and see. First, we need to check to see if it's a general path. If it's a general path, then we know it is also a general circuit. Let's start at F, go from F to G, to E, to D, back to G, then down to B, to C, which is over here, up to D, down to B, over to A, and then up to F. So yeah, that worked as a path, and since I started and stopped in the same place, it is also a circle. Now, what about whether or not it's an Euler path and circle? Well, did I cover every edge? And this is why color coding is important. Yes, I traced every edge in green, so it is an Euler path and an Euler circuit. Let's look at number 3. Number 3 could also be a circuit because it starts and stops at C. So let's check out and see if it works. So I'm going to start at C, go C to D, to E, to G, to F, A, B, and back to C. So it worked as a path. It's a circuit because I start and stop in the same place. Is it an Euler path and circuit? Well, no, because I can see with my color coding that I did not travel those inner 3 edges. So it is not an Euler path and circuit. So hopefully you're starting to see the difference between just a general path and circuit and a more specifically defined Euler path and circuit. Okay, let's look at the next page, number 5. I'm given an example of a graph. It's a connected graph with 5 vertices, A, B, C, D, E. No loops, just a couple of curved edges here. This graph has a possible path. Trace this path with your pencil and determine if it's an Euler circuit. Well, could this path be a circuit? First question. Yes, because it starts and stops at the same place. So get your pencil or your pen and trace that pathway and determine whether or not it works. And if it works, is it an Euler circuit? I'm going to pause the video and do mine, so you want to pause your video while you do yours. Okay. Hopefully you decided that no, it's not an Euler circuit. When you trace your pathway, the pathway works. We start at E and we end back at E. We go from E to B. Well, the only way to directly do that is this big circly edge out here. Then A, C, back to B, up to D, over to C again, and then up to E. Why isn't it an Euler circuit? Well, it's not an Euler circuit because we didn't travel that edge. We didn't travel over edge ED or DE. You can name it either way. But we didn't travel that edge, and for Euler, gotta do every edge exactly one time. So let's think about how paths and circuits, our definitions, fit together, and then we're going to draw that Venn diagram that represents them. Every Euler path is an Euler circuit. Well, no, because every path doesn't have to start and stop at the same place. Every Euler circuit is an Euler path. Well, that's true, yes, because it has to first be a path that starts and stops at the same place to be a circuit. Every Euler path is a general path. True. Every Euler circuit is a general path. True, because that just gets more specific. Every Euler path is a general circuit. Well, no, because remember, circuit defines it as starting and stopping at the same place, and an Euler path doesn't have to start and stop at the same place. Every Euler circuit is a general circuit. Well, yes, that's true. We learned that in that first chart we did on back on the other page. So let's think about those 4 different loops for general paths and circuits and Euler paths and circuits and how they should interact with each other. Well, we already know that in general, every circuit is a path. So that's our general Venn diagram that we drew for 13.1. Now we need to add in Euler paths and circuits and how they interact. Well, we know that every Euler path is also a general path, so it's going to be inside here somehow. And every Euler circuit is also a general circuit, so it's going to be inside that circuit loop. So let's start there. In fact, I'm going to kind of attach these. I'm going to say, you know what, this is my set of Euler circuits. Every Euler circuit is a general circuit. Every Euler circuit is also an Euler path, and so if it's that Euler path loop, let me change colors, is going to include those Euler circuits and then some Euler paths that are not Euler circuits. So you see I made this loop here so that it includes my Euler circuits, doesn't include circuits that aren't Euler circuits. I tried not to make that include anything else. So my Euler circuit loop is inside my general circuit loop. My Euler paths include my Euler circuits, but no general circuits. And they're all within general paths. All right, let's look at this next page, Euler's theorem. Our Euler's theorem that we're interested in deals with these circuits and paths. The following statements are true when I have a connected graph. So they're only true for connected graphs. If my graph is disconnected, this doesn't work. Euler's theorem has 3 main points. If a graph has exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. So if I need to find an Euler path, first I'm going to check and make sure I have exactly 2 odd vertices, not 3 odd vertices, not 1 odd vertex, but exactly 2 odd vertices. And then I know that that Euler path is going to start and stop at one of those 2 odd vertices. So it'll start at one of the vertices that's odd degree, and it will end at the other. If a graph has exactly no odd vertices, so it only has even vertices, then it has at least one Euler circuit. And if all the vertices are even, since we know it has at least one Euler circuit, we can start that circuit at any of our vertices because they're all even. Number 3, if a graph has more than 2 odd vertices, we don't have any Euler paths or Euler circuits. So if we have more than 2 odd, I got nothing. No Euler paths, no Euler circuits. Based on that information, how do you answer this? True or false? A graph with no odd vertices has at least one Euler circuit. Well, that's true, because if it has no odd vertices, that means they are all even. And the second point of Euler's theorem tells me that if they are all even vertices, we have at least one Euler circuit. Use Euler's theorem to determine whether or not there's an Euler path and or an Euler circuit. Note, if a graph has an Euler circuit, can I say that it doesn't have an Euler path? Well, no, because every Euler circuit is an Euler path. So if it has an Euler circuit, then I also have Euler paths. Okay, what if I have no odd vertices? Well, if I have no odd vertices, they're all even, right? And point 2 said if they're all even, I have at least one Euler circuit. And since every Euler circuit is an Euler path, I got those 2. What if I have exactly 2 odd vertices? Well, that is that first point of Euler's theorem. If I have exactly 2 odd vertices, I have at least one Euler path, no Euler circuits. So at least one Euler path, no Euler circuits. If I have more than 2 odd vertices, I don't have anything Euler. No Euler paths, no Euler circuits. What is the best answer for number 11? Now, I'm not a big fan of best answer questions, but this is definitely a best answer question. Read your 4 choices, and what do you think is your best answer here? Well, according to point 2 on our graph, if I have no odd vertices, so every vertex has an even degree, then I know I have an Euler circuit. But notice at the very, very top, when we started Euler's theorem, we pointed out that this is only true for connected graphs. So the best answer to this question is C. It is connected and every vertex is even degree. All right. The next page, we have 4 multiple choice questions. I want you guys to go through and answer those. Pause the video, answer 12 through 15, and then come back to check and see how you did. For number 12, it states that I have 102 even vertices and no odd vertices. This doesn't matter. This is what's important. According to Euler's theorem, if there are no odd vertices, I have an Euler circuit. Number 13 says I have 53 even vertices and 2 odd vertices. Again, this number doesn't matter. This number does. 2 odd vertices mean that I have an Euler path, but not a circuit. Number 14 tells me I have 45 even and 3 odd. Again, this 45 number doesn't matter. What matters is 3 odd vertices tells me I don't have either a path or an Euler path or an Euler circuit. So number 15, I want a graph that has a total of 11 vertices. Now this time this matters because I have to figure out how they work out. And it has an Euler path but no Euler circuit. Well, what do we know about graphs that have Euler paths but no Euler circuit? According to question 13, if I have an Euler path but no Euler circuit, I need 2 odd vertices. So if I have 2 odd vertices and a total of 11, that means I will have 9 even vertices. All right, examine each graph. Use Euler's theorem to determine if each one has an Euler path, and then determine whether or not it has an Euler circuit. Because of the way the theorem is structured, the very first thing we do is check to see whether or not they are all connected. So double check and look. It looks like all 3 graphs are connected. I'm going to color code these. We're going to start with graph 1 first, but the very first thing you have to do is find the degree of all your vertices, because Euler's theorem focuses on whether my vertices have even or odd degree. We're going to find the degree of the vertices for graph 1, and then I want you to pause the video and you do graphs 2 and 3 before you come back to check. So for graph 1, E is a degree 2 because I can leave E in 2 directions. B is degree 1, 2, 3, 4. C has degree 3. D has degree 3. And A has 1, 2, 3, 4. Those are the degrees for the vertices for graph 1. So pause your video while I pause mine. Finish finding the degrees for the vertices for graphs 2 and 3. Okay, so compare your degrees of your vertices that you wrote down to what I got. Make sure they match. And if they don't, double check yours because I'm certain mine are right this time. For graph 1, so we're looking just at graph 1. What do we have? Well, we have 5 vertices total. 2 of them, exactly 2, are odd. According to our Euler's theorem, if I have exactly 2 odd vertices, I have at least 1 Euler path, but no Euler circuit. Okay, let's look at graph 2. For graph 2, I have 1, 2, 3, 4, 5, 6, 7 vertices total. 1, 2, 3, 4 of them are odd and 3 of them are even. That gets me nothing. So when I have more than 2 odd, I know that I have no Euler paths or Euler circuits. So I know I don't even need to worry about looking. In graph 3, when I look at my 1, 2, 3, 4, 5, 6, 7 vertices, I see that they all have even degree. Well, if they all have even degree, then I have at least 1 Euler circuit. If I have an Euler circuit, we know that it is also an Euler path. So that's an and symbol. So because the degrees are all even for these vertices, I know I have an Euler path and I know I have an Euler circuit, and every Euler circuit is an Euler path. Now we're going to talk about Fleury's algorithm. Fleury's algorithm helps us figure out how we're going to find, if we have an Euler path or circuit, how we can find it. So we start by looking at Euler's theorem and thinking about whether or not we can expect one, and then we use Fleury's algorithm to help us find it. So Euler's theorem tells us that if we have exactly 2 odd vertices, we have that path, that Euler's path, and we're going to start at the odd vertex. You start at one of the odd vertices and you travel to the other odd vertex. That's going to be where you stop. If there are no odd vertices, then you can start anywhere because that means they're all even. Those are your 2 choices. As you're trying to go through, you number the edges as you trace the graph according to the following rule. Now, I don't usually number my edges. I usually write out the vertices as I go through them, and then I trace the edges. Totally up to you. This suggests that you mark traveled edges with a dashed line. I just use colors. If you have a choice of edges, you choose the edge that is not a bridge. You save the bridge to last if there's no other option. So think about this algorithm. If a graph has no odd vertices, where do you start? Well, you start anywhere. They're all even. You know you have an Euler circuit, and you can start at any one of the vertices. If I have exactly 2 odd vertices, where do I start? Well, I start at an odd vertex, and I'm going to travel to the other odd vertex, and that makes my Euler path. Euler path only, not an Euler circuit. What if the graph has more than 2 odd vertices? Where do I start? Well, I don't. It's not going to work. I'm not going to find an Euler path or an Euler circuit if I have more than 2 odd vertices. True or false on 19. If I'm using Fleury's algorithm to find an Euler circuit, should I always begin with an even vertex? That's true. Because if I'm finding an Euler circuit, then all the vertices are even. My basic rule in Fleury's algorithm about a bridge is that I'm only going to travel the bridge of the untraveled part of the graph if there is no alternative. That's the best choice of those answers available for that question. Okay, so let's find some Euler paths. Now, you don't have another student to work with, so you just get 2 shots at this. We're going to do one, and then I'm going to encourage you to do another one. I have a couple that I have listed off that we're going to try. Euler path. So if I'm finding an Euler path, where do I start? That's my first question. Where do you start? Where do you start? Well, if I'm looking for an Euler path, I'm going to start at an odd vertex. What are my odd vertices? E and C are my odd vertices. They are degree 3. The other vertices all have even degrees. So I'm either going to have to start at E or I'm going to start at C. So for this path, I'm going to start at E. And then over here, I'm going to do a path where I start at C. I want to encourage you really to try to see if you can do this one on your own. Remember to save bridges for last. So you're going to look to see if you have any bridges. I don't think we have any bridges in this one. All right, so this is the pathway, the Euler pathway that I followed when I started with E. I know I start with E, I'm going to end with C. Now, I've already done this. That's why I'm just copying it down really fast. I know I need to start with E because that's what I said. That means I have to end with C. So I think I went around the outside first. Yeah, I think I went around the outside first. So I went from E to G, down to H, up to F, back around to G. So I did that curve. Then I went curved around to D. I went up to B, over to A, back to B, down to C and up to A back around to D. Then I curved around the outside to F, E, D, and back to C. This is an Euler path because I traveled every edge exactly one time. So here's my challenge to you. I want you to pause the video. I want you to start with C. That means you're going to end with E. And I want you to see if you can travel an Euler path on this one. Okay, if you struggled with that one, hopefully it was a productive struggle and you accomplished your goal. This is the Euler path that I found from C to E. I didn't go ahead and trace it, but you can feel free. Hopefully you traced yours. If you didn't succeed with yours, try mine. Do a different color, try mine. Use Fleury's algorithm to find an Euler circuit. on this next one, and then copy a path from another student and try again. So again, we've got two different copies of the same graph. So I'm encouraging you to do two different circuits. The question, as always, is where do you start? Well, if I have an Euler circuit, I know that all of the vertices are even, and so I can start anywhere with any vertices because they're all even vertices. I want to make sure that for an Euler circuit, I travel every edge and I start and stop at the same place. I'm going to give you one. I did one that starts and stops at F. I'm going to give it to you, and then I'm going to show you. I literally sat and played with these, made false starts, had to go back and redo until I got the hang of them. So I'm going to give you this one, and then I want to encourage you to try and find, oops, that should be B, to try and find one that starts with a different letter for this second graph. So let's travel this one that I found. I start and end with F. So F is here. I went from F to I to K, up to J, back to I, down to D. Then I went back to F, B, around to C, D, H, J, L, down to G, then up to K, down to E, back over to G. Where did I go from there? G to K? I've already done G to K. Oh, E to G. There I am. A, B, E, and then F, and I've traveled all of my edges. Okay, let's see about the next page. We've got just this last page left dealing with Euler paths and circuits. This time we have a map, so we're looking at it geographically. So let's look at our map and see if we can figure out a representation using graph theory. So we're told to draw a graph to represent the map. Use Euler's theorem to determine if a family could visit each state, crossing each border only one time. If a path or circuit exists, use trial and error or Fleury's algorithm to find it. So what we're going to have to do is we're going to have to build our graph and then look at the degree of each vertex to see whether or not this is possible. How many states do we have? Well, Michigan is split by the Great Lakes. This is just one state. So Michigan just gets written down once. So that's 1, 2, 3, 4, 5, 6, 7 states. I've got, let me move this over a little bit. I've got Minnesota, Iowa, and Missouri, 1, 2, 3. Then I've got Wisconsin and Illinois, 1, 2, 3, 4, 5. And then I've got Michigan and Indiana. Those are 1, 2, 3, 4, 5, 6, 7 states. Before we can figure out the degree of each vertex, I need to draw my connections. Well, Minnesota borders Wisconsin and Iowa. So I need to draw an edge from Wisconsin into Iowa from Minnesota. Iowa borders Minnesota, we just did that. Also borders Wisconsin, Illinois, and Missouri. So Iowa goes to Wisconsin, Illinois, and Missouri. Missouri just touches Iowa and Illinois. Illinois connects to Wisconsin and to Indiana. It does not connect to Michigan. Illinois does not because there's a Great Lake there. Michigan touches Indiana and Wisconsin. So there's my graph. Now I need to look and see about the degrees of each vertex. Well, I've got a 2, 1, 2, 3, 4, 2, 4, 4, 2, and 2. So every degree is even. What does Euler's theorem tell me about all even degrees? Well, it tells me that I should have an Euler circuit. So I think the answer is going to be B, but I need to check this circuit to see if it actually works. B is only the answer if it works. If it doesn't work, then nothing, this isn't possible. These answer choices A and B aren't going to happen. Okay, so let's do this. We're going to start anywhere. Oh, no. We're going to start at Indiana. We need to see if theirs works. So let's trace. We're going to start at Indiana and go to Illinois, then Missouri. So Indiana to Illinois to Missouri to Iowa, to Minnesota, to Wisconsin, then back to Indiana, different border, down to Illinois, back to Wisconsin, to Michigan, and then home to Indiana. Yep, that works. So that is an Euler circuit. Number 24, our last problem here, wants you to use this floor plan, find two different paths that pass through each doorway exactly once, and tell whether or not your path is an Euler circuit. Our first challenge is going to be to get the graph together. So we have four vertices, A, B, C, D, and we have edges that represent doorways. So D has a doorway to C and a doorway to A. B has two different doorways into A. So B goes to A two different directions. C opens onto D and onto A. C opens to D and to A. And that's it, right? We have 1, 2, 3, 4, 5 doors, 1, 2, 3, 4, 5 edges. Let's look and see what our vertices, what degree they are. Okay, so we have paths that are circuits. We absolutely do. So yes, our Euler paths are going to be circuits. See if you can come up with a path that's a circuit that starts and stops at each of those vertices. One that starts and stops at A, one that starts and stops at B, one that starts and stops at C, and one that starts and stops at D. Pause the video, see what you can come up with. I'm going to list mine. Okay, so here is one possibility each, starting at A, B, and C. And then I gave you two possibilities of an Euler circuit that starts and stops at D. I can leave D and go to A, or I can leave D and go to C. The pathway is different depending on which way I head out first, but notice that they're just reversals of each other. So I could do the same thing with these others as well.